From the time of Galileo through the 20th century, physicists spent a lot of time being kind of confused about exactly what light is. So Galileo figured out that it was very fast. Newton was convinced that light was a particle. Light can reflect off of things, but then again, so can a ping pong ball. Light can diffract, but so can a bullet fired into water. As it rapidly changes speed, it'll bend. In 1800, Thomas Young figured out that light could do some things that particles simply cannot. Light can diffract, which is to bend around objects, more on that later, and it can also interfere. And particles can't do that. You can't overlap two baseballs and have them cancel out and not be a baseball anymore, or reinforce and become a double baseball. It doesn't work that way. So we actually had a situation where Newton was fundamentally incorrect. Sort of, until Einstein had something to say about it. But anyway, that's a topic for another time. We were largely confused about exactly what light was. Enter the 1800s. Michael Faraday was someone who did not possess a formal education. He could read and write, but his math ability was actually pretty low. But he managed to get a job as a helper to the head of the Royal Society, and through that job, ended up becoming one of the greatest experimentalists in mankind's history. And Michael Faraday invented the motor. He invented the generator. He discovered electromagnetic induction, where changing magnetic fields can create voltage, it can create electricity. And that's how the generator works. And he found a lot of intertwined relationships between electricity and magnetism through the early 1800s. And in 1845, he discovered something very, very interesting. If you take light and you pass it through a polarizing filter, then so if this filter is aligned vertically, then the light comes in and it's going in all sorts of different directions, but when it comes out, it's doing this, right? It is polarized vertically. Well, Faraday figured out that if you take a magnetic field and you align it along the same direction that the wave is traveling, that the polarization of the wave will actually rotate. It'll rotate around. And so he found that light waves were actually influenced by magnets. That is often called the Faraday effect. Go figure. It's also sometimes called the magneto-optical effect, because magnets affect light, magneto-optical. But the Faraday effect was a really good indicator that light is electromagnetic in nature. And later that same year, Faraday wrote a paper that was not even really a hypothesis, it was more of a hunch that light is actually a jiggle of electromagnetism. He lacked the mathematical ability to actually formulate this in a way that other scientists would accept. And he spent the next 20 years being kind of frustrated with this idea he had in his head that he couldn't get on paper in a way that people would believe. Well, in 1865, another Englishman, James Clerk Maxwell, who was a phenomenal mathematician, created 4 equations that we call Maxwell's Equations. And you don't really need to know the details. In fact, you can't do the math at this level in your mathematics career yet. But this math, which Faraday certainly couldn't do, actually demonstrated that Faraday was right. What are these 4 equations? The first one says that electric charge can exist by itself. You can have just a positive charge, and that the electric field will point away from it everywhere. If you have a negative charge by itself, then they'll point inward. The second equation says that that is not true of magnets. It says that for a magnet, anytime you have a north pole, you also have a south pole. Anytime you have a south pole, you have to have a north pole. Magnets are dipoles, while electric charge can be a monopole. The third equation is a mathematical formulation of what we call Faraday's law. It says that a changing magnetic field can create an electric field. And the fourth equation is a variation of Ampere's law, which says that a changing electric field, a moving electric charge, will create a magnetic field. So we have this idea from the math that a changing electric field can create a magnetic field, and a changing magnetic field can create an electric field. And we didn't really have the technology at the time to demonstrate that. So Maxwell looked around in nature for a way to help him out, and he thought, you know, if you have alternating current, a metal rod hooked up to an alternating current, it should create waves. And when he used his equations and he used this high-level math that he was doing to figure out the speed of those waves, he figured out that those speed is equal to 1 divided by the square root of 2 constants, which the AP2 class will be familiar with, mu naught and epsilon naught, the permittivity and permeability of vacuum. If you take 1 over the square root of mu naught epsilon naught and you calculate it out, you get 2.9989 times 10 to the 8 meters per second. You get exactly the speed of light. Maxwell, 20 years after Faraday came up with his idea, proved that it was true. Light is an electromagnetic wave. 22 years after that, Heinrich Hertz demonstrated this in a laboratory in 1887. He found that you could create energy in this manner and that energy had a frequency. It could be reflected, refracted, and diffracted, and that it would interfere. He found that it could be polarized as well. He proved in the lab Maxwell's assertion that Faraday was correct. So now we know that what we see as visible light is really only a tiny portion of a huge spectrum of light that we call the electromagnetic spectrum. And the only thing that makes visible light special is that our eyes can see it. And other living things can actually see electromagnetic waves of other frequencies that no human has ever experienced. Tragically, Hertz died when he was only 36 years old of blood poisoning. He was an incredible experimentalist, and who knows what he could have discovered had he lived longer. I mean, within 15 years of Hertz's discovery, Guglielmo Marconi had built a radio that could send communication across the Atlantic Ocean, and that was the beginning of mass communication in the modern era in 1901. So what is it then that we now know about light? Light is extremely fast. Light does not require a medium. It can travel through space without vibrating any matter because it's actually vibrating electromagnetic fields. Light is a transverse wave. It can be polarized, and that's proof that it's transverse. Light is electromagnetic. If you actually look at the amplitude of the electromagnetic wave, they're perpendicular to each other, this electromagnetic field and this magnetic field. If you look at the ratio of their amplitudes, E over B, that exactly equals the speed of light. The energy of a light wave is shared equally between those two fields. And finally, light waves carry not only energy, they also carry momentum. That means, yes, you can push things around with light. More on that detail later. Light gets really interesting, and when we talk about modern physics, we'll get into some of the kind of mind-blowing stuff that Einstein and some others opened the doors to. Now, I have through my entire career been kind of lazy, and I tend to call all of electromagnetic radiation light, and that's probably not great. Regents, you have an electromagnetic spectrum on your reference tables that looks like this, and it looks a little better maybe in color. And the electromagnetic spectrum is really just a listing of how we have categorized various types of electromagnetic waves based on what they can do. Very, very long waves are radio waves, and then when you get down to about 2 meters to 1 meter to 1/4 of a meter, we call those microwaves. And then if you get even shorter still, we get infrared waves. Things that are warm to the level of things we normally see on Earth radiate pretty strongly in the infrared spectrum. We can wear night vision goggles and see that. We actually all glow. I'm glowing right now, but I'm not glowing in visible light. I'm glowing in infrared light. And then we have this tiny, tiny little sliver of the spectrum, which is visible light, the things we can see. And that goes from the lowest energy red up to the highest energy blue, going with, or violet if you prefer, going through Roy G. Biv. Once you get to violet, higher energy than violet, which our eyes can no longer see, we call ultraviolet. Above that, we have X-rays. We didn't know what they were when we first discovered them. When Rontgen discovered X-rays, he didn't know what they were, and X is the variable in math, so X-ray it is. Later we learned They're just another type of light. And even higher than X-rays, we get gamma rays, something else we didn't know what they were when they were first discovered. Gamma rays often shoot out of radioactive nuclei, but it turns out all it is really, really high energy light. If you're given a wavelength or a frequency, it's really easy to calculate the other one using v equals f lambda if you realize that v is c, the speed of light, 3 times 10 to the 8 meters per second. And finally, it's also useful to remember sometimes that right in the middle of the visible spectrum, what we can see, the wavelength there is 550 nanometers, and that corresponds to a frequency of 5.09 times 10 to the 14 hertz. If you remember, I mentioned that when we were talking about refraction and the index of refraction and why this chart specifies that frequency. That's the average for visible light. And it's a very bright yellow-green color, maybe a little more yellow than this. That's why a lot of fire trucks and things in some countries are starting to change to this color rather than red, because our eyes see this very well. That yellow-green color is the brightest color that the sun puts out, and go figure, we evolved eyeballs that see that color the best. There is a huge universe of things that humans cannot see. Like I said before, some animals can. Honeybees can see in the ultraviolet, and flowers look different in the ultraviolet. They have patterns that we can't see with our eyes. When we look up in space, we now use computers and digital cameras to look at nebulae in various different spectrums, and we can see things like maybe possibly evidence of black holes or gamma rays or X-rays coming from things that otherwise just look kind of fuzzy and white to our eyes. It is incredible how much is out there that human senses just can't pick up. We have sound, and now we have light, where we have this very limited range. And with sound, we're pretty good. With light, we're extremely limited. We have this narrow band of what our sun mostly puts out. And then everything else out there, we can't even detect. And believe it or not, all of this is only half of the story. Light has a wave nature, but it also has a particle nature. And the particle-wave duality is something that we're going to talk about more with modern physics later in the course. In any case, that's it for wave basics. In our next series of videos, we're going to move on to some specifics about wave optics.